सर यहाँ पे सिर्फ concavity की point होगी.
So you know the another sign of it is that when you look at the graph of it, you know it's changing the concavity. While in previous two cases the concavity is not changing actually. So if it is concave up, you know it's always concave up. It's concave down. It's concave down actually all the time. ठीक है? Is it making sense? थोड़ा सा. Now keeping in view, so there are three things which are playing an important role. Okay? So number one, so you're gonna have a first derivative and second derivative test in higher dimension as well actually. Okay? Now imagine in your head a dome actually. Okay, let's make it. Let's make one. Okay, let's make it in GLF. Okay. Let's make it. So what should be the equation of it? So x squared plus y squared. Okay. That's really the x squared plus y squared actually. Okay. Aha. That's another thing. That's really the projection of it. That's the domain of the projection. Sometimes you want to find what's the domain of this guy. That's the domain of this guy. You can really, it's a shadow of it. Anyway, but that's an illusion. It's not a disk. So you're looking from the top. Actually, it looks like
top view.
You're looking at it from a perspective where it looks like a
from
disk.
top view, sir.
Anyway, so think about it. And so, what are you going to do? What are you going to do with it? What would be the meaning of having, for example, a minimum or maximum of this function actually? So let's just start analyzing it. So what should be the first thing that we should care for? What do you think? We should have smoothness actually. Okay? But the trouble is, okay, so it makes sense to have only a minimum value for it. For example, let's talk about the minimum value first. Okay. So how does the minimum? What would be where is the minimum value that this function x squared plus y squared takes? So it's really at the origin. So it takes the value 0. So the potential point where you want to, which could be the critical point in this case, is going to be this point AB 0, 0. Trouble with this picture is that here you had before and after actually. Okay? Here you don't have before and after because you can reach to the origin in many crazy ways actually. Okay? So in other words, you can ride on this line and reach to the origin. You can ride on some other line and reach to the origin. Are you getting the point? Or you can make a different curve and reach to the origin. So you have multiple ways of reaching to the origin actually. Question: if we would like to describe it, what would be a good way to say it?
So fresh derivative अगर 0 Jacobian compute करें वो 0
Okay, Jacobian 0. That's the first case actually. Yeah. That's the first case. The Jacobian must be 0. And instead of taking tangent line, let's take a tangent plane actually.
Yes, sir.
What happens with it? But the trouble is that for tangent line we had something like slope actually. But have we something like slope about the tangent plane? We have something what we call the direction cosines or something like that. But we haven't done it, so let's not get into it. What should we do? Here's the thing. Let me make it negative. Let me make it, for example, minus so that we can really. Okay, so what should be done? So see, that's a two-dimensional sphere. Like the plane is two-dimensional. So this object is two-dimensional. You need two quantities. Okay. So what you are looking at the moment is the graph of P of uv. That's really the P of uv. But from where you are choosing uv to get this graph? So that is your uv actually. So that is your, what you call the domain. So you are picking the points from uv and giving them a height actually. Okay. So there are only two principal directions here. Okay. Like this direction of the u coordinate, another is the direction of what you call the v coordinate actually. And if you take any other direction, not a big deal. Why? Because any other direction other than u and v can be written as a linear combination of, this u and v actually. Okay? So you don't have to worry about this. So you just have to look at what you call, uv direction. For example, if you are in x, y, z, so just look at the x, y, what do you call directions? What happens with the x, y directions? And what do you mean by what happens with the x, y direction? What happens with the, okay. So here we have a derivative, but here we should have Fresher derivative. The Fresher derivative is a bigger quantity, so you can compute the Fresher derivative through something. What are those? The partial derivative. The partial derivatives. Okay? The partial derivatives. So if you compute your partial derivatives in the principal direction, in other words, think about it. So I want to reach to the origin, but through one of these lines actually. So one of these lines. Maybe I want to, for example, sit on this line. Okay. So what is this? So you may call it, for example, say this is x-axis, and let's call this z axis. This is y-axis. So this line is really, what do you call? So when I'm moving on this line, actually, in other words, if I am choosing the inputs from this direction, and I'm not moving, and what do you call, along y, another coordinate. Actually, if this is y, then I'm not moving along x-axis. And if this is, what do you call, x-axis, then I'm not moving along the y-axis. So just call this direction as the principal direction. So as I'm choosing my inputs more and more and more closer to the zero, the corresponding outputs are getting closer and closer and closer to the. In other words, what we are saying is that draw a tangent line to this curve actually. So this curve, or this coordinate which takes you to the origin actually, and look at its slope. So the partial derivative is what? So we saw that you take this surface, okay, and you take this plane and slice it. So it's going to produce a curve on the surface, and then you really, you draw the tangent line on that curve. Okay. So in other words, if I take a plane and slice it, so it's going to produce this curve, isn't it? And if I draw a tangent line to this curve, okay, the slope of that tangent line is going to be the partial derivative with respect to whatever this green direction is representing, x or y or u or v, doesn't matter. Are you getting the point? So in other words, instead of looking at, taking the Fresher derivative means that you want to approach to this point, but from all possible direction actually. So one thing is there is no need to do it, just do it in two principal directions and try to reach to the origin. Rest of the directions are really the combination of these two directions actually. So you don't have to do it. Okay? Though the Fresher derivative is going to give you information for sure. Okay. So think about it. If this is representing what do you call x-axis, okay, and that's really, what do you call the line, okay. When you are moving on this line, you are moving only what do you call along x-axis. So the points are the values of the coordinates are changing, but not with respect to y, only with respect to x-axis actually. Are you getting the point? So do we have something like dome or something like? कोई है ऐसी चीज? कोई चीज ऐसी? Something like that. Okay. Okay. Let's take this. Let's take this. So this is not really, a good example, but you will treat it. Okay. So what I'm saying is this. So here you have these lines which are really, what they are doing. The principal direction line. Okay. Right. And the base is really, So in other words, if you see the projection of it, so it will be a plane actually, a rectangle in two dimension actually. Are you getting the point? Now think about it. So if on a one principal direction I'm just moving actually, so here I'm just looking at the inputs that are being chosen from only one direction. For example, if you call this as x-axis and this as y-axis, you're not making any turn or movement along y-axis actually. Okay? So what essentially I'm saying? I'm saying take your tangent line, do the same what you did there. Take your tangent line and look at it and see that how, it's changing its slope actually. And that slope is really partial derivative. Okay? In other words, if you imagine in your head a tangent line that moves along this curve, so what will happen with the slope of it? Okay. So what will happen with the line? So it's gonna do what? It's gonna gain more and more slope actually. The slope is really increasing. So यहाँ slope come है, so you have this line. So you have a more negative slope. But if you come down, so here you're going to have a more negative slope if you choose a point here. But if you choose a lesser point, you're going to have a more positive slope of this line and more positive slope, and eventually you reach to this point, and then you go from the other side, and hence the slope is always increasing. Is it making sense? So what does this mean? And what would be the partial derivative at the origin? So in other words, roughly what you can do is that if you want to, for example, okay, so that would be one way to do it. But if this point is really a critical point, it should give you 0 from the other direction as well. Okay. So how about if I choose the direction along what do you call this red line, or y-axis keh lein or v-axis keh lein, whatever you call it, and I move along this curve. So what will happen with the slope of it? So it will, it's the slope is increasing. The slope of the tangent line is gaining more and more slope and becoming. So here it goes negative and then becomes positive actually. Are you getting the point? Okay. And the point is that if you choose any other direction and try to reach to this point, is really the combination of these two directions actually. So this PU and PV, okay, really span, what do you call the tangent space at this point actually. Okay. So in other words, no matter where you draw a tangent, you can write it as the combination of PU and PV. Okay. So what we can say, what we can agree on this actually, that if a point is a minimum point, okay, if a point is a minimum point, then the partial derivatives with respect to u and v or x or y must be zero. So that would, not minimum, but the critical point actually, So it's enough to say that the partial derivatives of x and y with respect to x and with respect to y is 0. In other words, the gradient is 0. So if the partial derivative of the function are 0, it really means that the gradient is 0. And if the gradient is 0, what you actually are saying that the Fresher derivative is 0. Because, for scalar fields, the gradient becomes Fresher derivative. Or Fresher derivative becomes gradient. Are you getting the point? So that would be the first way to say that, you have, what do you call, a critical point. And I can revert this picture. I'm going to have a similar kind of a definition for the critical point for all. So the critical points are what? In such kind of a picture where the partial derivatives are 0. And convince yourself that why they are 0. Because the partial derivatives are the slopes of the tangent lines. Okay? When you are moving along to this, what do you call, the point of the minimum value, okay, through the principal direction. Principal direction u and principal direction v. Are that?
Yes.
Okay. Alright. What should happen with the second derivative? It should be the same actually. Think about it. So if this is a minimum point, okay, so there is a bit different story than previous. Okay, don't get into the proof of it in this class, but we will do that in next class. But essentially, what you are doing is that you can have almost an analogous behavior to the one dimension actually. That okay, a point is going to be the minimum point if the FUU is positive actually. Okay? Okay. So F is not positive. FUU is minimum has a positive. Yes, should be positive. Okay. And not only FUU, but in other words, second order derivative with respect to the u, but second order derivative with respect to v must also be positive. Okay? And hence, what do you call? You can have a similar kind of analysis for negative factor. Is it making sense? So you're doing the precisely same analysis, but
सर अगर partial u जो है वो 0 होता है और partial v 0 नहीं होता तो फिर
that's not a critical. That would be kind of a saddle point actually. I mean, if you remember, we had a saddle. Okay. So in other words, the function would be decreasing. The point on the surface would be the minimum value. If you are somehow really, no matter what direction you take, you are always going down and then coming up. Okay? Whether I go this way or any other way, I'm always going down and then coming up. And you're going to have an opposite for the maximum. But you can have an interesting situation actually. Think about it. So let's put a minus actually. And look at it. Now the origin becomes an interesting point. So what does that mean? So if you go along the one principal direction, 0 to 9, दोनों principal directions. But if you go along the one principal direction, on a, for example, curve, the partial derivative is what you call is gaining the slope. So it's not FUU is becoming more and more positive actually. It's positive. But if you go along this, so you have a kind of a valley actually. What happens? Okay. Along this point.
Getting more and negative.
So this really the slope of the tangent line and the FV is becoming more and more negative. So you have a different behavior. So if you go along one direction, you're going up, and if you go along other direction, you have. So you're going to have a valley actually. So that's really a valley. So you call such point as a saddle points. So these are the saddle points, which were really inflection points previously. So now you call them a saddle point. And why you call it a saddle? Because this is really a saddle. Saddle समझते हैं? A horseman sits on a saddle and घोड़ा सवार है. वो जिस जगह बैठता है, जहन जिस पर बैठता है, like you call that place as a saddle and it has this shape actually, funny shape.
सर और इसमें एक क्रीज लफ्ज भी था, उसकी मतलब
क्या मतलब क्रीज?
इस पे सर जो बुक था हम पढ़ रहे थे कैलकुलस में, उसमें सैडल पॉइंट पे और कोई एक क्रीज आ रहा है, क्रीज वर्ड आ रहा था उसकी
ट्रफ्स एंड क्रेस्ट,
CREASE
होगा कुछ ना कुछ मतलब. Anyway, is it making sense? ठीक है. So a critical point. So one thing is this point is still a critical point. In other words, the slope becomes zero no matter what direction you go actually. If u be zero or if v be zero. So it's a critical point actually. But this critical point gives you no, meaning actually. ठीक है? If someone is, coming from this direction, they're going to say, I'm trying to reach to a maximum value. Okay? And I'm making an effort to reach to the top actually. जो ऊपर से आ रहा है, what has happened with you, भैया? Where is the maximum? I'm going down. I'm moving along the gravity and, So, यहाँ से आ रहा है, I need to make an effort to reach here. यहाँ से आने वाला कहेगा, what effort? I can drop and I can reach here. Is it making sense? Okay. So let's formalize all this stuff. Okay. So now we have an intuition, and let me just write this in a what you call more concrete form. And maybe do one example. Okay. By the way, all these maxima or minima that you are having here, these are all relative maxima. So these are relative maxima. Can you differentiate between relative and absolute maxima minima in one dimension? क्या difference होता है?
सर जो ग्लोबल होता है ना वो एक पॉइंट्स पे भी एग्जिस्ट करते हैं.
So you have this extreme value theorem actually. Okay? So extreme value theorem tells you that if you have a function which is a good function but it's defined on a closed interval, then it's no matter what happens it's going to achieve a maximum and minimum. Okay? Either they are going to exist within this input interval. If they are not existing within that, then they must exist on the boundaries. And you can have something similar in two-dimensional as well. Okay. Okay, so let me put roughly what we call the so-called second derivative test. Okay. And surprisingly, it's a bit different than apparently the first derivative test we have there, but it has a closer relation. Okay. So let me put formal definitions. Okay. So I'm going to say, let's define this in 2 dimension, and then you can have a similar kind of a thing in 3 dimension and higher dimension as well. So maybe will be, so if practically when you are trying to solve, for example, practical problems, we are mostly concerned with the functions with the 2 inputs actually, because when you have a functions with the 2 inputs, its graph becoming, it exists in 3 dimension actually. Okay, so the most of the surfaces that you see are the result of what you call 2-dimensional function. Okay? 2-dimensional function means that the function, the scalar field defined on an R2, okay, as a part of the R2. So in other words, if I have a function f of xy, I have a function f from u to r, and maybe the u is in subset of R2, and I have a point AB in its domain. I'm going to say that this point AB is relative minimum, okay, if what happens? If you look at, so if you take a point, okay, in the domain of the function f, which is in the neighborhood of AB. So AB is a fixed point, so you have this domain and AB is this point actually. And you take a point that is really in the neighborhood of, what do you call, so xy can be anywhere around this point AB, okay? So if xy is a point in neighborhood of AB, can you predict what should be the relationship between f of xy and f of AB? If AB is really a maximum.
less होना चाहिए सर ये.
हाँ जी?
f of x of y less than होना चाहिए.
It should be less than or equal to f of AB. Okay? So you don't have to memorize the definition, you can really explore it. ठीक है? And similarly, we can call this AB to be a relative minimum. Okay? If f of AB is what? Is less than or equal to f of xy on all neighboring points of the point AB. Okay? In other words, that
Sir, ये
in the neighborhood of AB, the function is what? Decreasing. Okay? Well, here the function.
सर ये पहला रिलेटिव मैक्सिमम है सर.
So greater than.
हाँ, sorry, it should be maximum, minimum. अच्छा, पहला अगर minimum है.
तो फिर वो सिंबल चेंज होगी, ग्रेटर देन होगी.
Greater होगा सर, नीचे से.
नहीं.
बस रिलेशन उसमें.
Minimum के केस में उलट होगा.
और जैसे वो ऊपर वाला हो.
So if it is minimum, it should have greater than or equal.
all the values around.
और maximum हो. अब ठीक है?
जी सर.
अब ठीक है. So
अब सर.
if AB नहीं.
सर ये सही नहीं.
नीचे भी
बस ये ग्रेटर होगा. सही. एंड वो पॉइंट सब वैल्यू से ग्रेटर.
yes. ठीक है. We have this small definition. Let me define what do I mean by a critical point. So I'm going to say AB is the critical point. So what do you think what should happen? Okay. So if you compute the partial derivative of x and evaluate it at AB, and you compute the partial derivative of xy evaluated at AB, it should be 0. So otherwise you go in one direction or other direction, you should always get the 0. That is, you can put this together, that the gradient of f at the point AB must be 0. Okay, so that's the definition of what we call a critical point or a stationary point. ठीक है जी. Now here is something what we call the second derivative test. So I'm writing it without proof, but maybe we can discuss this in next class. But it makes sense when you're gonna see from the pictorial point of view. Second derivative test. Okay. So you say that suppose you have a critical point. AB is a critical point. So in mathematics, quite often you associate criticality with when the thing is changing its behavior. In many of situations when you're going to have this word critical, mostly you're going to mean that okay, it's a kind of a point where something was happening before it and something different is happening before after it. Anyway, so critical point. Okay. and F is C2 class actually. That is F